Hi Year 13, today I'm going to talk to you about NMR spectroscopy. First of all, you've probably heard of MRI as a diagnostic technique in medicine. It uses strong magnetic fields and radio waves to produce detailed images of inside the body. NMR uses the same principles and we use it to investigate the structures of compounds. Now, NMR will only work if the atoms that we're investigating have got an uneven number of particles in their nucleus. So in organic chemistry, we use carbon-13 and Proton NMR to investigate the structure of molecules. So what does an NMR spectrum tell you? Well, there will be a number of peaks on the spectrum, which will tell you the number of different environments. The chemical shift, which is the resonant frequency of a nucleus relative to a standard, sounds a bit confusing, but you don't need to worry about that, is affected by the atoms and bonds in the environment around the nucleus. So it tells us the type of environment that the proton or carbon nucleus is in. And the chemical shifts are measured relative to TMS, or tetramethylsilane. And that's this molecule here. It's a silicon with 4 carbons and 12 protons. So the carbons and the protons are all in equivalent environments. So it gives us a strong signal, which we call 0. And everything else is measured relative to that. Okay, also I just want to mention quickly, deuterium is often used as a solvent, or deuterated compounds are used as solvents in NMR because they don't produce a signal. Obviously hydrogen, because we use it in NMR, has got an unpaired proton in its nucleus, whereas in deuterium there's an additional particle in the nucleus, so it's not got an uneven number of nuclear particles and does not give a signal. Right, so on your data sheet you will have this information, okay, and these are the carbon-13 NMR chemical shifts relative to TMS. And you can see carbons just next to carbons tend to be quite low down on the chemical shift, whereas when they're next to oxygens, as in carbonyls or in aromatic compounds, then we see quite big chemical shifts. So let's have a look at an example. Okay, here we have a molecule of propan-1-ol, and we've got 3 different carbons, and you can probably see that they're each in a different environment. Okay, and here is the NMR spectrum that we would get for this molecule. So if we have a little look, we can see obviously there are 3 environments. We've got one peak at 64 parts per million over here, which is going to represent this carbon. We've got a peak at 27 and a peak at 12, which will represent this carbon and this carbon. It's not always possible to tell between 2 in a very similar environment, but you will get 2 different peaks. Okay, so you look at the number of peaks for the number of environments and the types of carbon from the chemical shifts. Here we've got another molecule. This is propan-2-ol. So what do you think the NMR spectrum would look like for this? Well, here it is. There's only 2 peaks this time, because hopefully you recognise that we've got 2 equivalent carbons. You couldn't tell those 2 apart, and we've got one obviously in a different environment, and there's the information about where the peaks are and their chemical shifts. I'll let you have a look at that at your leisure if you wish. Okay, so carbon NMR is quite simple, tells us 2 bits of information. I'm going to talk to you about Proton NMR. The scale is similar. It's not the same. It tells you the horizontal scale tells you the chemical shift. Yeah, and as with carbon NMR, it's on the yellow sheet. Again, the number of peaks tells us the number of different environments, but in addition, The relative peak area tells us the number of protons in that environment. So let's just have a quick look at a couple of compounds. We've got 3-hydroxypropanoic acid. How many hydrogen environments can you see there? And 2-butene. How many proton environments can you see there? Well, hopefully you've worked out that with this one we've got 4 environments, 1, 2, 3, 4, and with this one we've only got 2 because these 3 and these 3 are in the same environment. Oops, I was getting this the wrong way. Oh, no. As are these 2. Apologies. Okay, so let's just look at a Proton NMR in a bit more detail. Okay, so here's our molecule that we've just been looking at. Now, a table like this is a really useful way of summarising the information from a Proton NMR. There's relative area, functional group, and obviously chemical shift. Now, later on we'll add a fourth column for splitting patterns, but don't worry about that just now. Okay, so first of all, cut this hydrogen here is an OH. The relative area would be 1 because there's only 1 of that type, and the chemical shift, well, you can see for OH proton it's quite massive, so it could be anywhere along there. Next we have got proton number 2, and you can see here we've got 2 of those, so that means the relative area is 2. Now this is an OCH because obviously it's next to a carbon which is next to an oxygen, and the chemical shift is in that region, 3 to 4.5. And then we've got this hydrogen, which again we've got a relative peak area, we've got 2 of those. This is next to a carbon which is next to a carbon with a carbonyl group, so that gives us a chemical shift of between 2 and 3. And then finally we've got this hydrogen, which is the hydrogen in a carboxylic acid group, which gives us a chemical shift of between 11 and 12. And this is what the actual Proton NMR would look like. So basically this represents this, and you would be able to get all this data from this NMR and be able to link it to the structure. Okay, it says on your whiteboard, but on a bit of paper or something, here is the other molecule we looked at. Perhaps you could take a minute to predict the peak area, functional groups, and the chemical shift for this molecule. Give it a minute, and here we go. Well, we've got proton number 1. We're going to talk about this one. We've got 6 of those, so our relative area is 6. Functional group is just it's just a alkane, so our chemical shift is going to be in that region. And then we've got 4 equivalent protons here, so our relative area is 4. Again RCH, and so again in that sort of area. So our NMR would just be 2 peaks quite close together. Right, finally, splitting patterns. This is what a more detailed Proton NMR looks like, and we're going to talk next time about what these splitting patterns mean, because they give us some extra information. Okay, bye for now.